Is that my clicker? Yeah. I have to get oriented here because I thought I was coming to talk at an AI conference. And I was imagining like 200 nerds with green hair and a Coke. And I was wondering what the bankers were all doing here. And it's literally there's a bank sign on the stage. So I'm going to have to get calibrated. So I queued the talk up for people who watch YouTube at 4x. And I have 54 slides. So but we're going to work through that as quickly as possible. So just hang on, and if anybody wants to get a drink or something, do it soon. All right, so I joined Intel a year and a half ago, and I was somewhat surprised to find out that Moore's Law was dead, and somewhat famously, so everybody's talking about it being dead. So first of all, I joined the Moore's Law company, so that's a kind of a sad career move. It's like joining a rotary phone company. So that's bad. And then a friend of mine and head of servers at Google came over and talked to one of our exec sinks. There's a room like this with 500 people in it. And he said Moore's Law was dead. It's kind of a drag. They're one of our best customers. So I asked him if I could return the favor and talk about Moore's Law at Google. So I went over there and I said, search is dead. Yeah, and I gave part of this talk. So, and Moore's Law is really interesting because it's a complicated phenomena, and it drives an industry in a way it's kind of wild. Imagine, like, the laws of physics change every 2 years. Like, we have twice as many transistors, right? Which means designs are harder and more complicated. Like, things keep changing. The fundamental thing is everything keeps changing. And I had an engineer, we're talking about some bugs, and he said, well, this is a bug because this changed, this is a bug because this changed. And I said, actually, no, you have a job because it changed, right? There's a bug because the architecture screwed up, it wasn't staffed, or something happened. So, you know, it's a weird thing. Like, our business drives change, and then business models like Google, the reason Google was pissed off is because if Moore's Law slows down, their business model is predicated on Moore's Law compute, because that's how they imagine what they do next. So let's go through some slides. Now, for AI, I really like this one. I like the bitter lesson thing. From a hardware engineer point of view, it looks to me like early optimization, right? Because the hardware is moving really fast, and the algorithms are moving really fast. And sometimes you get overly focused on, like, some of the details. Meanwhile, so many things change. But I do want to convince everybody here that Moore's Law is going to keep going and continue to drive change in radical ways that you can sort of depend on. And we'll see what happens with the slides we go through. So here's a slide Google showed us, which is kind of sad. So, and there's a bunch of features to this. For a long time, we had Moore's Law scaling the transistors. We had scaling the frequency. It drove performance fairly easily. But as we build more and more complicated processors, there's a whole bunch of things that scale by n squared. And there's also the expectation set. If you believe you have to go double performance every 2 years, it's a very different belief than performance is slowing down for some reason. And that often leads people to think about accelerators like, well, if general purpose computing isn't going fast, maybe we'll go to accelerators. But accelerators have a really interesting feature. Like history, we had floating point accelerators and vector accelerators. They got merged into CPUs. There used to be a thing called a sound card for older people, and that's now a software algorithm. GPUs have bounced around a lot, you know, accelerated with special purpose hardware, and then they went very programmable, and so on. And today there's 50 startups building AI chips to accelerate various parts of the algorithm. And what happens over the next couple of years is going to be really interesting. And I'll get at the bottom of the talk, I'll talk a little bit about computer architecture future and one of the problematic things about AI acceleration. I like this graph. We saw it earlier. There's been just an exponential super Moore's Law growth. And it's interesting when you look at the performance, the computers got faster, they got optimized for AI, people figured out how to marshal more computers, and they also tweaked the algorithm simultaneously. And it was an exponential, an explosive growth in computing. Now, some of that is mining the early low-hanging fruit. Whenever you have a new algorithm area, you know, there's a new data type, there's a new way of doing an execution engine, and you can get some easy steps that way. And we'll see what happens with this. The traditional Moore's law was more transistors, better performance per dollar, and frequency scaling. And we've seen a couple of those curves slow down a little bit. But recently, TSMC, a big fab, Samsung has a big fab, they announced a 10-year roadmap for about 4x every 5 years on transistor density with concomitant improvements on both power and area. So we're seeing this continue. The question is, how does it translate? And then what's actually driving it? So let's talk about that a little bit. And I do want to mention, so I joined Intel, and at Intel everything has an extra zero next to it. So my team is 10,000 people. And we're building 100 different computer chips. And every one of them is getting more complicated. So when Moore's law doubles the transistor count, you can say, well, we'll just put in 2 processors, or 4, or 8. What we actually see is the number of IP blocks that go in a chip is going up, and the complexity is going up, right? And our ability to design to that has to keep changing and scaling. So I like 2x2 matrices, and I made this one. For the bankers who don't know this, engineers always make a 2x2 out of everything, right? And the one axis says Moore's law is not dead or it is dead, and the other is you believe it's dead or you don't believe it's dead, right? And so if Moore's law is alive and you believe it, it's challenging. Yeah, that makes sense, right? We've been living that era for a long time. If you think it's alive but it's not, you're a little delusional. You may optimize a little faster than somebody else, but you know, there's a fundamental change in your business, because if Moore's law really slows down, the kind of computers we make will kind of turn into a race to the bottom instead of a race to complexity. This would be depressing. And by the way, there's so many headlines about this, and I'll show you a few. But you know, that's not my problem. My problem is I live in a Moore's law world with more and more devices and more IP, and we have to build to the complexity that generates. So let me tell you about that. Moore's law is basically relentless. Imagine everything you do every couple of years has to change. Top to bottom in an organization that's also trying to be effective. Super fun problem. And Moore's law is famously about the transistors. But if you look across the dimensions of computer architecture, the scaling is almost a scatter plot. 1,000 times more transistors per core, frequencies up 1,000. I'm a processor architect down there. It's only 10x more instructions per cycle. Proof costs 10 million times. I used to work with Craig back in the late 90s. We used to say it was a megawatt per teraflop. We now have a chip that's a watt per teraflop. 1 million times better power for the same number of operations. Everybody's seen this. Moore's law won't work at feature sizes less than 1/4 micron in 1988. My favorite was the everything that's been invented can be invented has been invented, 1899. So who the hell thinks this stuff? Does anybody believe this stuff? These guys do. Now this is really weird because Jensen runs NVIDIA. That's the Moore's law company. Somebody who's trying to shame Intel for not participating in enough big AI projects. His whole business is Moore's law, and he said Moore's law is dead. I don't really know why. I think they were late on a node and didn't want to be embarrassed. But David Patterson's a very serious professor, and he said Moore's law dead. So I went and gave a talk about Moore's law at Berkeley. He sat in the front row and took notes. It was pretty fun. There's subtle arguments about what's scaling and what's not, and I think that's more relevant. But the transistor scaling is kind of wild. So, my clock's moving way too fast. Let me just go through this. There's something called a diminishing return curve, and innovators all know what this is. You have innovation, accelerates, and it diminishes. And conventional thinking says, I can see the end of this change, right? Happens to everybody. And if you go look in terms of technology, there's one successive wave of diminishing return curves after another. That's what actually happens. software architecture IC design process. And people think, Moore said, we'll have twice as many transistors. And he said 65,000, we're now at 65 billion transistors. So he was off by a factor of 1 million, but he did call it in 1975. Like, that's the conventional belief. Moore's law drove something called Bell's law, which is every 10x you had faster, smaller computers, right? We went mainframe, mini, workstation, PC, mobile. These are huge transformations in compute. Kurzweil happily plotted this back to the 1900s, right? That we've been on a log linear curve of computer performance for over 100 years. And yet people always think Moore's law is dead. We actually live in an accelerating return curve world, right? But it's not one thing. So you look at a technology and you say, I see the end of that. But innovators have the next technology. So let's imagine that progress is actually a cascade of diminishing return curves, right? And we've been living in that world. Now, some of them are very different. Let me walk you through some examples. Transistors, we shrunk the transistors, we changed the material, the strain, and then new material, and then we went to a 3D fin architecture. They're very different technologies. If you look at the transistors, there's something called a planar MOSFET, and then a FinFET where we put the gate on both sides of it. Now there's gate all around, which lets us build both smaller devices with better control. And if you actually looked at them real size, the nanowire transistor you couldn't even see. We went from 6 micron devices to about 100 nanometer devices. I worked with Elon for a while, and he had this comment that I really liked, is first you figure out how you want the atoms to be, and then you figure out how to do it. Imagine this is the difference between being how constrained and what constrained. So you go look at a modern fab and you say, this equipment can only get so much better. You're not thinking about what's the physics of the devices you want to build and then building the environment to go do that. It's a very different way of thinking. And I'll just give a fun example. When we first started shrinking devices with optics, one idea is when we got to the limits of the wavelength, we made the wavelength a little shorter, and then we made it 10 times better than that. When the wavelength got too small, it started interfering with itself. So back in 1990, if you wanted to draw an X, you drew an X. But as the light interfered with itself, it changed the pattern, but you could reverse engineer what that transfer function is. So the masks got printed to generate the thing you wanted. So these are the masks to make an X as we got smaller and smaller. Right? Here's today what you see on a mask, and that's what it prints. We got 10x of that. Now the new EUV equipment has taken a 10x step on that. Does that make sense? So I asked my team to map out a factor of 100. Transistor down, how do we get 100x? So everybody thought Moore's law is dead. I thought 100 would give us some runway. And they came back 3 weeks later and they said, we have a path to 50. And I said, why don't you go work on that for a couple more weeks? So we can make the fins finer. We're going to nanowire, which is 2x. We're going to actually stack gate logic in the nanowire stacks, which is worth another 2x. And then we're going to do wafer-on-wafer stacking, so we basically build the wafers and marry them right together at the local metal level, and then we do die stacking, die-to-wafer stacking. Right? And one argument is, well, it's getting too expensive. The cost per transistor has been coming down so fast. EUV machines, when they first shipped them, was over $500 million, and they were relatively slow, and they had low uptime. They're under $200 million. They're getting better unbelievably fast, and the fabs are converting to EUV because it's less patterning than the fancy patterning I showed you earlier. Here's another example. NAND devices, famously, the cells are getting so small they only trapped 25 electrons and they were leaking out. So they stacked them with wire bond, which is literally sewing machine for high tech, where they stack the devices together. And then they went and built this. 128 layers of NAND devices stacked up vertically. And they made the devices a little bigger so the electrons stopped leaking out. Way more reliable, and we're not sure how tall that can go. They've been doubling this every couple of years. So I was going to make up a quote like this, but we found this one. It's more fun. So I just want to talk about the scalars a little bit. So I'm mostly a computer architect, although I like to build all kinds of systems and various things. And I was looking at this evolution. So way back in, the 1900s, we built computers with very short, simple pipelines. And then the pipelines got longer and then wider, and then we did something called superscalar. And this basically, I got my 2-minute warning. I only have 40 minutes to go. So this executes the code that the compiler generates relatively straightforwardly. If you look at a GPU, what you'll see is huge arrays of these simple processors, okay? Well, what modern computers actually do is they fetch a large number of instructions and they go look through the instruction stream and find the out of order, the fragments of the graph that they can issue out of order, right? And we went from 3 wide to 6 wide. A modern Intel processor has 20 execution units wide, a 500 instruction window. It predicts branches with 99+% accuracy and executes all that code out of order differently every single time. Like, the acceleration of this is just incredible. It runs 10 times faster than the old computers with 100 times longer memory latency, which for people who do math is like 1,000x. And then finally, we build computers in these complicated stacks. So as a processor designer, we have technology, devices, circuits, gates. We write RTL as a description of the computer, the marker architecture, the ISA. And one of the geniuses of the computer business is, as things get more complicated, we refactor this stack. Because as somebody mentioned earlier, Moore's law is exponential, and human brains are kind of flat. We're not getting any smarter. But the stack is getting deep, and that lets us do complicated things independently. Now, the accelerator world is really interesting because one of the ideas is, for fixed problems, we can collapse the stack and get a massive acceleration. But as you collapse that stack, your ability to program and innovate on it also gets limited. And that's the dynamic for AI that we're going to see, as you have acceleratable algorithms, but also deal with the complexities of that. Because what the programmers want to do is program, right? And I really like this graph because it means about 100 different things. Like, to write the Hello World program, it used to be a very simple program in assembly in C, and somebody noticed that if you wrote it in Python today, it's an exponential increase in number of instructions, right? So some people say we're getting less and less efficient. On the flip side, if you want to find a cat picture on the internet, you can write a very short program to do that today and marshal the power of 100,000 computers to find that in no time flat. You could never write that program in assembler. 1,000 people for 1,000 years couldn't type it in. Right? So the power of the abstraction stacks is really interesting. And Moore's law enables us to build these wildly complicated computers, right? And still accomplish our goals with human level intelligence to do the pieces. Okay. So people ask me a lot, well, how far is it going to go? So a modern transistor is 1,000 by 1,000 by 1,000 atoms. The fin itself is about 125 atoms wide, and we know that we can get that down to about 10, right, before you have serious quantum effects. So 100 by 100 by 100 transistor is about 10,000 times denser than today's. And we're going to go build them 3D, because if anybody's ever been in a big building, a 2D building's really, it's a lot of walking. 3D is the best way to get from point A to B, right? And we don't know how far we're going to go down, but it's pretty far down. So Moore's law is going to keep going for a while. And I just got to stop, and that's my last slide. So thanks, everybody.